Okay. This term we are ourselves.
Managed to derive. You've
Ouch.
jiggled it about so that you've got, because it equals 0, you've got the gamma terms, the Christoffel terms, expressed in terms of the metric tensor and first derivatives
It's my
the
neighborhood.
metric tensor. So what can you say about this Christoffel symbol? Firstly, it's not itself a tensor. It's in a sense, it's a correction term.
You don't need it to be this one if I'm
Christoffel
that
symbol
dude on the
will
news
be
that
equal
day.
to 0 in flat space. But it won't be equal to 0 in curvilinear time space or space-time. And you'll also notice that it can be expressed wholly in terms of the metric tensor and the first derivatives of the metric tensor. And you might ask yourself, why have we spent all this time trying to find a thing called a Christoffel symbol when it doesn't even feature in the Einstein field equations? You will not see the Christoffel symbol in that equation or those equations. And the answer is no, you won't. But that's because the Christoffel symbol is buried in the Ricci curvature tensor, and that's what we're going on to next. But first, I think it's possibly time for another break. Okay, so now we come on to curvature. If we're going to talk about curved space-time, we better understand what curvature means. Let us take a path in flat space. Flat space-time. My paper is flat. What you do is you take a vector. A vector, of course, will have magnitude and direction.
So far, nothing wrong.
And what you do is you what's called parallel transport it around the path. That means you keep the same length of vector and you keep it oriented in the same way, so it travels parallel to itself. So all of those lines are intended to be, my drawing may not make it quite so obvious, but they are intended to be the same length, and all of the vectors are parallel, so they just keep parallel to themselves until you get back to where you started. And of course, when you get back to where you started, your vector will be of the same length and it will be in the same direction, because it's always moved parallel to itself, so it will come back to where it started. Okay, all very well and good, but now let's take a cone.
This is a rock. The difference? Described in a 400-pound garden
path
and a one-hand pebble piece of garbage.
For illustration purposes, as you can see, it's a curved cone.
Every time.
But what I can do is I can cut down the side of the cone and open it up. So if I make a cut along one line, I can then open the cone up and it becomes flat and it has that kind of shape. So let me recreate the cone. I just bring those two lines together. When it's a cone, that edge is joined up. So in a sense, this edge here and this edge here are the same line.
You're telling me it's
the
a circle.
same point.
Your dinner.
On the cone.
Could have been this.
So let's just draw what the cone looks like.
I'm saying this.
When you open it up, you cut.
And if you fold that
down
all up, just cut your shit.
This point here, and you open it
up.
It's
a circle.
And
That's
you get
to be a circle.
Shape that looks like it's a circle.
On the IMA
with
program,
a
you can make
slice
that roll out.
Taken out of it. That's the cone. Just a quick reminder. There it is, the cone. And remember that the line OA and the line OB, when they are in a cone, are the same line. It's that dotted line. Now I'm going to do a bit of parallel transporting.
I'll give you that card if I need to be there
remember
and
where
I
the
wasn't.
vector
I'd be
was.
like,
Let
I
me just
wasn't
take
there.
that
That
B
meant
out of the
something,
way.
didn't it?
Put it there.
Like if I was there charging your ass out, you know.
I'm going to have a vector which continues the line OB. So it's just a straight continuation. And now I'm going to parallel transport that vector around the cone. Remember, it stays the same length, though mine may not. It always stays parallel, and we keep going until we get to A, and we stop because A
it made one
is
loop around
point B.
And
Remember,
so what this
they are
meant
the
was
same
they were good.
points
They pulled
on the
off a
cone.
run. But the same thing as
But
ramping
what
up
has
the
happened?
hydrogen
Well, the
collider to the
length of the
collision.
vector is the same. But
That
the
number isn't good
direction
until
of the
it's
vector has changed.
stable.
You can tell it's changed direction
Still
because
amping up.
I started it as being an extension of the line OB. And OB is the same as the line OA. Remember, it's this dotted line here. So if the vector were to be in the same direction, it should end up like that. But it didn't. It ended up like this. It's gone through an angle. So although the length has remained the same, the direction of the vector has changed. And that is a measure
So
of
we
curvature.
can do the
If
matrix
you
and monkey
parallel
blood.
transport a
How many
vector
monkeys we can
around
explode,
a
how hard we can
surface,
explode those monkeys.
and you don't get back, and you get back to the same position, remember position A is position B, you get back to the same point, but the vector has changed direction, then you've gone round a curve.
Pens roll comment.
So that's how we're going to define curvature. An angle change in the vector when you parallel transport it around a surface. If it's a flat surface, as we showed, no change
Because
in
what
direction.
that is by a
If it's a
whatever
curved
in here,
surface,
screaming black
it changes
hole that just
direction.
firewall destroys
Now I'm just
you.
going to take a slight diversion and a pause to deal with two definitions.
Think about this,
The
boss.
first is what's called a commutator. Commutators are written like this: square brackets,
I know,
A and
that's
B.
why it's weird.
All
You
that
like
means
normally you'd be
is
like, I'd hit you with the
AB
garden hose or spray
minus
with one, but I
BA.
can't do it for some reason right now.
A times B minus B
figure it
times
out,
A.
Bob.
Now, of course, if we are simply talking about pure numbers, then that will equal 0. 3 times 2 minus 2 times 3 is 0. But the point about commutators is they don't always equal 0. And I'm particularly going to look at one, which is the commutator of d by dx.
Why would I get in the way of this?
And some function of x, that's my commutator, and I'm going to show that that actually equals
Yeah, but it's fun
dfx
to always challenge it because
divided
some
by
asshole's always ready to go,
dx.
and then you go, alright.
Doesn't
Okay,
equal
we're
0.
good so far.
So let's just do the quick proof. Remember that the commutator is AB minus BA, so it's going to be that times that minus that times that. So let's just write that out. That's going to be d by dx of fx minus fx times d by
All
dx.
green.
Now you've got to apply a d by dx to something, so let's just call it v.
Catch 'em go.
But here we've got the differentiation of a product, and just as we did before, we can say that dAB is equal to BDA plus
You can't say it, can you,
ADB.
Gunner?
Doesn't matter which way round you do it. Differential of a product, BDA plus ADB.
I
where
know,
this
it's a
is
tough
A
one, man.
and this
That's
is
Rubik's
B.
Cube.
So consequently, this term here, using this formula here, will equal B, which is V, times dA, which is dfx by dx, plus
That's
A,
Noah loves you. Big, wet,
which is
squishy kiss
FX.
waiting for you under this rock. You can,
times dB, dV by dx. That's that term, and we must remember that term there, which is minus fx dV by dx. And you'll see that that term and that term are equal, so one minus the other is 0, and you're left with v times dfx times dx. Well, v is something we simply inserted, so we can now take that out, and now you've got that the commutator
now you know.
is equal to dfx
And
by
that
dx,
commutator
which is
has a lot.
what we
Sounds
wanted to
almost
show
like
in the first
electricity,
place.
doesn't it?
So let's now
that thing was
take
hooked up to your
two
balls and maybe it gives you a
coordinates,
zap.
which do not necessarily have to be at right angles. This is the x mu coordinate. This is the x nu coordinate. And I'm going to have a distance, which I'm going to call dx mu. And I'm going to have a distance this way, which is dx mu. So a distance dx mu in the x mu
Looks like
coordinate
skid steer
system,
safety video
and
to
a
me.
distance
I see
dx
it.
nu
Slip, trip,
in the
and
x
falls.
nu
Pyramid.
coordinate. What I'm going to do is construct a parallelogram from that. So essentially it's going to be a parallelogram
Manage your
where the
training
length of these two are going to be dx mu. And that's the
Same sheet
same
of
there.
paper. It
And the
is.
length of these two sides, dx nu. So far, so good. And now I'm going to do a parallel transport around this path. We're going to go from A to B to C to D and back to A again. But I'm going to call the return point
here and tell
A
you and
prime,
Simon to figure it out for me.
because I'm not sure that we're going to get back. The vector will be exactly the same when it gets to A prime. So the vector at A prime may not be the same as the vector at A if we have gone round a curved surface.
If you ask the question,
Now let's
why
just
couldn't we be
take
quantum
two
physicists to tell you
paths.
you
Consider
can
two
graph it?
paths. The first is VC minus VD. That's essentially what we're talking
Can't
about
help
there
it.
is the difference between the vector at point C and the vector at point D.
Didn't you eat that marshmallow?
And compare that with the vector at point B and the vector at point A.
Now,
Now,
you haven't written one bit in
we are
the English
going
language,
around a
not one
flat
word.
surface,
Not one word to
then
find other than some brother's name. I gotta go find him
C
in
minus
this box
VD
and see him do shit.
will
Watch him.
equal VB minus VA, and that whole term will equal 0.
You're doing good. Keep up the good work.
But what this is actually representing is the differences in the d mu direction, because that's the or dx mu direction, because that's the directions.
So what
that
they
we're
challenge
moving
you with, oh, you couldn't.
here.
Really?
Similarly, if you take
Why do you think
the
you need
C
to break what
minus
this fine brother
VB,
did at the floor
which
today?
is this path here, minus VD minus VA prime, you get the difference in the dx nu direction. Because that's that path there and that path there, they're parallel.
In standard model
In
core
flat
system.
space there would be no difference, but in curved space there might be,
Thick break.
and you're now looking at the difference in the d nu direction.